Welcome, general chemistry students. This is the third video in week 11, and we are going to explore the Arrhenius equation. So at the end of this video, you will be able to determine how temperature affects rates of reaction. And you're going to do this by identifying what's called an activation energy. And this comes from using the Arrhenius equation. And we're going to use the Arrhenius equation in two ways. We're going to use it by graphically determining the activation energy, and I'll show you how to do that. And also by using what's called the two-point Arrhenius equation, where you have a set of data at two different temperatures. Okay, so really what the Arrhenius equation is all about is how does temperature affect the rate of reaction. So we know that changing the temperature is going to change the rate, is going to change the rate constant. It will speed up, but it doesn't change the overall rate law. And this Arrhenius equation was first discovered by a man named Savant Arrhenius. All right, and he determined that the rate constant was proportional to this frequency factor, and this exponential that is the activation energy divided by the gas constant times temperature. Okay, so when we're doing this, we need to pay attention to the units. The temperature is in Kelvin. The gas constant is 8.314, and that's joules per mole Kelvin. So let's talk a little bit about these terms. So A is called the frequency factor, and really it's the rate of the reactant energy as it approaches the activation energy. Okay, so it's measured as a rate. And the activation energy is a measure of the energy it takes for molecules to react. So how much energy does it take for the two molecules to come together and form product? That's the activation energy. Okay, so what that is so imagine you have this reaction where you have, in this case we have hydrogen and oxygen forms two water molecules. So on an energy scale, we have our energy of reactants. As the reaction moves forward and the energy increases, eventually we're going to make it to a spot called the activation energy. And you can think of the activation energy as kind of an energy barrier. How much energy do I need to get to in order to proceed to product? And you can see once you have gone over that barrier to the activation energy, it's only downhill from there. Okay, so once you've gotten to the activation energy, you will proceed to product. Okay, so that's what that means. All right, so here is a measure of the activation energy, all right, from the energy of reactants to that barrier. And from here to here, all right, this distance is the enthalpy of that reaction. So you can see here, this is an exothermic reaction. Okay, so let's talk a little bit about that activation energy. So the activation energy, I said, can be thought of as an energy barrier. What is the barrier you have to surmount in order to proceed to product? So the activation energy is really that amount of energy. And at the top of that activation energy is what's called a transition state or activated complex. Okay, so or a transition state. They're both the same thing. So once you've gotten over that activation energy, that complex that you've formed is called the transition state. All right, and in this activated complex, you have a series of partially broken and partially formed bonds. And this complex is really, really high in energy. And so to relieve itself of all this extra energy, it's going to proceed to products. Once you've gotten to the activation energy in the transition state, the only thing left to do is go to products. All right, so let's look at this reaction. So this is the isomerization of methyl isonitrile. So methyl isonitrile is going to rearrange into what's called acetonitrile. Okay, so essentially your N and your C are exchanging places. All right, so how does this work? Well, what's got to happen is that bond between the methyl group, all right, so I'll just draw a line here, between the methyl group and the CN group, the nitrile group, has to rotate because we're going to flip that nitrogen over to the carbon. Okay, so it has to weaken the bond, and that NC group has to rotate. So for this reaction to occur, you must break a bond so that you can then form a bond. Okay, so we're breaking bonds, we're forming bonds. All right, so what this might look like in terms of our activation energy is here we have our reactant right here, and here we have our product. This energy it takes to break that carbon nitrogen bond, so we're weakening that bond and rotating. Okay, that is the activation energy. So as the reaction begins, that carbon nitrogen bond begins to weaken, and that CN group starts to rotate. Okay, so now at the activated complex or the transition state, we have these pseudo bonds, right? So we have our complex where that CN group is starting to rotate. So we have broken that carbon nitrogen bond, and that CN group is rotating. That's at the transition state. All right, once you have surmounted the transition state, now the only other thing to do is proceed to product. Okay, so the only thing here we need to do is proceed to product. And when we do that, the difference between the reactant and the product energies is delta H, or the reaction, or the enthalpy of the reaction. And you can see here that the reaction here is exothermic because the product lies lower in energy than the reactant. So really I would say 5 things to think about on this reaction coordinate diagram. Where is the reactant? Okay, this is our reactant. Where is the transition state? That's right here. Where is the product? The product is right here. What is the activation energy? Well, that's the energy from the reactant to the transition state. Okay. What is the enthalpy of the reaction? Well, that's the energy of the reactant to the product. Okay, that's the enthalpy of the reaction. All right, and the transition state is where you have these partial bonds, the weakening of the bond and the rotating of that CN. Of course, and the activation energy is the difference between those. All right, so let's look at the frequency. Okay, so the frequency is the number of molecules that begin to form the activated complex over a given amount of time. So this acts like a rate constant. Okay, so that's what we talked about as the frequency factor. Okay, so let's look at the Arrhenius equation again. So the frequency factor acts like a rate constant. So it represents the rate of the reaction energy as it approaches that activation energy. Okay, so as we approach that activation energy. And of course, the higher the energy barrier, the larger the activation energy, the fewer molecules that have enough energy to overcome it. Okay, so we're still thinking of the activation energy as a barrier, right? So the larger that barrier is, the fewer the molecules that have enough kinetic energy to surmount that barrier. All right, so the extra energy has to come in the form of kinetic energy. Okay, really important here. in the form of kinetic energy if we want those molecules to start to collide and form product. All right, so what's the strategy here? We can see from the Arrhenius equation that temperature is involved here. So what we can say then is increasing the temperature increases the average kinetic energy. So we know that, we've seen that before. So therefore, increasing the temperature will increase the number of molecules, all right, with sufficient energy. Okay, so we're raising the temperature. Now we have more molecules with sufficient energy in order to overcome that energy barrier. At the same time, according to our Arrhenius equation, if we increase the temperature, we will then see an increase in the reaction rate. So here we have more molecules that can surmount the barrier. Therefore, we have an increased rate of reaction. Okay, so we've seen this diagram before. So this is an example of the thermal energy distribution. And in blue is temperature 1, that's a cooler temperature. And in red is the temperature 2, and that's the warmer temperature. And you can see that there's these fraction of molecules and energy. So given a certain temperature, there is a distribution of energies. Okay, and so if we defined the activation energy as being right here, we can see that there's a lot more molecules in the higher energy that can get over that energy barrier than in the cooler energy. So we can see that if we raise the temperature, we have more molecules, because there's more kinetic energy, that can surmount that energy barrier. All right, and so what's going to happen? Well, you're going to get increased rate. All right, so from the Arrhenius equation, raising the temperature increases the rate of reaction. Okay, so let us take the Arrhenius equation, and we're going to take the natural log of both sides. And when we do that, we come up with an equation that we could form into a line. So let me show you what I mean. So if we plot the natural log of the rate constant versus 1 over t, that means then that we should have a slope of minus the activation over the gas constant plus b, which would be the natural log of a, which is your frequency factor. So from taking the natural log of both sides, now we have an equation that forms a line. And we love lines in chemistry. So we're going to plot natural log of k versus 1 over t, and we can get the frequency factor out, and we can also get the activation energy out from that. All right, so here we're going to say that y is our natural log of k, and x is our 1 over t. One thing to keep in mind is that 1 over t is in Kelvin, okay? So lots of times you're going to get data that's in Celsius, all right? But when you plot it, it needs to be in Kelvin. All right, and then the slope of the line is negative activation energy over R. So if we want to solve for the activation energy, we would merely just take the slope times minus 8.314, and we would get the activation energy in joules. All right, and of course the y-intercept is the natural log of A, so we would take e to the y-intercept. That will give us our frequency factor. And remember, the frequency factor acts like a rate constant. Excuse me. All right, so here we have some data. So we have taken a series of measurements at different temperatures, and we've measured their rate constants. Okay, and so we can plot this data and determine, well, what is the activation energy? What is the frequency factor? Okay, so when we do that, we're plotting again the natural log of k versus 1 over t in Kelvin. And we get an equation for the line because this is linear, right? So our slope is minus 1.12 times 10 to the fourth, and our y-intercept is 26.8. So we can use those values to determine the activation energy and the frequency factor. All right, so given the slope and the y-intercept, first let's solve for the activation energy. So we have our slope times our gas constant. That gives us 9.31 times 10 to the fourth joules per mole. But what you'll notice is that activation energy is usually measured in kilojoules per mole, and it really can range from tens to hundreds of kilojoules per mole. Okay, so 93.1 kilojoules per mole is right in the range of what we would expect an activation energy to be. All right, and then if we solve for the frequency factor, we take e to the y-intercept, and we get 4.36 times 10 to the 11th per molar per second. Okay, so if we look at these units, what that says to us is that's a second order rate constant. All right, and it's second order because we can think of these reactions as being bimolecular. You have to have two things that come and collide in order for you to get a reaction. And that's what the frequency factor is talking about, like how many molecules are colliding frequency. Okay, so it's like a second order rate constant. Okay, so imagine we just have 2 points. So we don't have a whole set of data, but we only have 2 points. Well, we can do that too using the two-point form of the Arrhenius equation. All right, so here we're going to take the natural log of the K2 over K1, and that's equal to the activation energy over R times 1 over T1 minus 1 over T2. Okay, so really important to pay attention to what you're calling 1 and what you're calling 2. Recognize that K1 goes with T1 and that K2 goes with T2. Okay, really easy to mix those up. If you mix those up, you will not get the correct answer. All right, so let's work on a problem where we can use the two-point form. So here we have a rate constant at 701 Kelvin, another rate constant given at 895 Kelvin, and we're going to find the activation energy of this reaction. Okay, so we're going to use the two-point form. Again, keep in mind K1 and T1 go together, and T2 and K2 go together. Okay, and really what we're going to do is we're going to use that two-point Arrhenius equation in order to find out the activation energy. So we're going to plug in numbers. Okay, so here again, K1 goes with T1 and K2 goes with T2. All right, so let's do that. So we know that K2 is 567 and K1 is 2.57. So we're going to take the natural log of that, and that's equal to EA, this is what we're trying to solve, divided by the gas constant, and then 1 over T1, which is 701, and 1 minus 1 over T2, which is 895. Okay, so we're just really plugging in numbers here. And when we solve for the activation energy, we get 1.45 times 10 to the 5th. Keep in mind again that usually you see these in kilojoules per mole, and so we end up with 145 kilojoules per mole. So remember I just said, well, typically these activation energies are between tens to hundreds of kilojoules per mole, so what we see here is right on par with what we would expect to see. All right. So the answer here is reasonable. Always good to check to make sure that your answer is reasonable. All right, so one more problem. So kind of a rule of thumb that chemists have is that the rate of reaction is going to double every 10 degrees in temperature. So this is what I was taught early on as a graduate student. So let's check to see if that's the case. Or better yet, let's see what the activation energy would be if that were the case. All right, so we're going to use the 2-point Arrhenius equation, and we're going to make, we're just going to choose arbitrary numbers. So we have T1 at 300 and T2 at 310. So we're just raising the temperature 10 degrees and seeing what happens. And so the rule of thumb is that the rate of reaction doubles, so we can make K2 really just 2 times K1, because we're doubling. All right, so we have these numbers. So we've thought of T1 and T2 because we're just raising the temperature. We're going to find that activation energy. Again, we're using the 2-point Arrhenius equation. All right, so when we do that, 2K1 over K1 simplifies to natural log of 2, so that's pretty simple. We're finding the activation energy, and we know the gas constant. And we can take 1 over 300 minus 1 over 310, and we get 1.075 times 10 to the minus 4. Okay, so we just rearrange the equation, and we get 5.36 or so times 10 to the 4th. Again, kilojoules per mole, 53.6. Okay, does that seem reasonable? Well, so I've said twice now that the activation energy should be between tens and hundreds of kilojoules per mole. So reasonable, right? All right, so most activation energies are tens to hundreds. So this answer seems pretty reasonable. So that rule of thumb is actually pretty good when it comes to determining how temperature is affecting the rate. So about every 10 degrees, the rate is going to double, is a chemist's rule of thumb. All right, so that is the end of video 3, talking about the Arrhenius equation. Thank you.